Imagine this. It's December 22nd, 2032. The night sky is clear, and billions of eyes turn upward as a streak of light hurtles toward the moon. Not a shooting star, but a 200-foot-wide asteroid named 2024 Yr4, packing the punch of 1,000 nuclear bombs. What if it slams into our celestial neighbor, shattering the silence of space and unleashing a storm of debris that could cripple our satellites, disrupt global communications, and turn the heavens into a hazardous junkyard?
But here's the twist you never saw coming. Right now, in secret labs and hidden silos, the United States and China aren't just watching. They're arming nuclear missiles, not for war on Earth, but to blast this cosmic intruder out of the sky. Is this the dawn of a new space race or humanity's desperate gamble against extinction? Stick around as we uncover the shocking scenarios, the hidden preparations, and the mind-bending questions. Are we ready to nuke the stars, or will the stars strike first?
The looming shadow of Asteroid 2024 Yr4, potential lunar impact, terrestrial consequences, and global nuclear defense preparations. In the vast expanse of our solar system, where celestial bodies dance in intricate orbits, the discovery of near-Earth objects, NEOs, often serves as a stark reminder of humanity's vulnerability to cosmic threats. Asteroid 2024 Yr4, initially detected by the Asteroid Terrestrial Impact Blast Alert System Atlas in late 2024, has emerged as a focal point in planetary defense discussions. This approximately 55 to 60 meter, 180 to 197 feet wide space rock, sometimes colloquially referred to as Asteroid Atlas, has captured global attention due to its calculated 4% probability of colliding with the Moon on December 22, 2032. While initial assessments briefly raised alarms about a potential Earth impact, estimated at around 3% before being refined, the asteroid poses no direct threat to our planet. Instead, the concern lies in the indirect repercussions of a lunar strike, which could unleash a cascade of debris into the Earth-Moon system, endangering satellites, space missions, and orbital infrastructure.
This video delves extensively into the potential scenarios of a 2024 Yr4 lunar impact, exploring its effects on the Moon and subsequent implications for Earth. It examines the scientific, technological, and geopolitical dimensions of planetary defense, with a particular focus on nuclear deflection strategies. Drawing from recent studies, simulations, and historical precedents like NASA's Double Asteroid Redirection Test, DART, we will analyze how nations such as the United States and China are preparing nuclear-capable responses. Relevant materials, including data from NASA, the European Space Agency, ESA, and peer-reviewed papers, underscore the urgency of these efforts. As we stand on the cusp of what could be humanity's first real-world test of asteroid deflection on this scale, the narrative of 2024 Yr4 highlights the intersection of astronomy, international policy, and existential risk management.
Characteristics and trajectory of Asteroid 2024 Yr4. Asteroid 2024 Yr4 is classified as a near-Earth asteroid belonging to the Apollo group, whose orbits cross Earth's path. Discovered in December 2024 by the Atlas Survey, a network of telescopes designed to detect potentially hazardous asteroids, it measures roughly 50 to 70 meters in diameter, comparable to the size of a 20-story building. Its mass is estimated at 200 to 300 million kilograms, depending on its composition, which likely includes rocky materials with possible metallic elements. Traveling at an average speed of 13.9 kilometers per second, about 31,000 miles per hour, the asteroid's kinetic energy upon impact would equate to 5 to 6 megatons of TNT, hundreds of times more powerful than the atomic bomb dropped on Hiroshima, but negligible on a planetary scale. Orbital calculations, refined through observations from telescopes like NASA's James Webb Space Telescope, JWST, in 2025, have eliminated any Earth impact risk for 2032 and beyond. However, the asteroid's trajectory brings it perilously close to the Earth-Moon system. Updated models from NASA and ESA indicate a 4.3% chance of lunar collision, with the probability subject to further refinement as more data accumulates, potentially not confirmed until 2028. This uncertainty stems from factors like the Yarkovsky effect, where uneven solar heating subtly alters an asteroid's path over time. Simulations using tools like NASA's Sentry Impact Monitoring System project that, if unaltered, 2024 YR4 could intersect the Moon's orbit during a close approach in late 2032.
Potential impact scenarios on the Moon and effects on Earth. A collision between 2024 YR4 and the Moon would be a spectacular yet contained event, given the Moon's lack of atmosphere and immense mass, 7.34 times 10 to the power of 22 kilograms. The impact would release energy equivalent to a multi-megaton nuclear explosion, excavating a crater 500 to 2,000 meters in diameter and up to 400 meters deep, depending on the angle of incidence and lunar regolith composition. For context, this crater would be similar in scale to Arizona's Meteor crater on Earth, but far smaller than lunar giants like Copernicus, 93 kilometers wide. A head-on impact might produce a symmetric, bowl-shaped depression with radiating rays of ejecta, while a grazing strike could create an elongated scar and disperse material more widely. The immediate visual spectacle would be profound, a brilliant flash visible from Earth if occurring on the near side, potentially outshining the full moon for seconds. This would be followed by a plume of vaporized rock and dust, detectable by infrared telescopes for hours. Critically, the Moon's low gravity, escape velocity of 2.4 kilometers per second, would allow significant ejecta, estimated at 100 million kilograms of regolith, rocks, and fragments, to be hurled into space. Some debris would escape entirely, while other portions could enter temporary orbits around the Moon or unstable paths within the Earth-Moon system. For Earth, the direct hazards are minimal, no tsunamis, earthquakes, or atmospheric disruptions, as the energy pales compared to historical events like the Chicxulub impact 66 million years ago. However, the secondary effects could be substantial. In the short term, hours to days, re-entering debris might trigger an intense meteor shower with thousands of shooting stars per hour, visible globally during nighttime. Larger fragments would burn up harmlessly, but the event would provide a rare astronomical bonanza for observers.
Over medium to long terms, weeks to years, the debris cloud poses risks to space infrastructure. Micrometeoroid flux in low Earth orbit, LEO, could increase by up to 1,000 times, heightening collision probabilities for satellites like Starlink constellations or GPS networks. The International Space Station, ISS, if still operational, or future lunar gateways might require enhanced shielding or evasive maneuvers to avoid punctures. Historical analogies include the 2013 Chelyabinsk meteor, which injured over 1,000 people from its airburst shockwave, though 2024 YR4's debris would be sparser. In low-probability variants, if the asteroid fragments pre-impact due to tidal forces, as rubble pile asteroids sometimes do, multiple strikes could broaden the debris field, amplifying risks. Overall, while temporary and manageable, these effects underscore the interconnectedness of lunar and terrestrial space environments.
Planetary defense strategies, from kinetic impactors to nuclear options. Humanity's arsenal against NEOs has evolved from passive observation to active intervention. The cornerstone is kinetic deflection, exemplified by NASA's DART mission in 2022, which successfully altered the orbit of Dimorphos, a moonlet of asteroid Deimos, by 32 minutes through a high-speed collision. This billiard ball approach, where a spacecraft imparts momentum to nudge the asteroid off course, proved viable for smaller threats with ample warning time. Follow-up missions like ESA's Hera, launched in 2024, have provided detailed post-impact data, refining models for future applications. For time-sensitive or larger asteroids like 2024 YR4, nuclear deflection emerges as a last resort. This involves detonating a nuclear device near the asteroid to vaporize surface material, creating a thrust that alters its trajectory without full fragmentation, avoiding the creation of multiple hazards. Simulations from Lawrence Livermore National Laboratory suggest a 100-kiloton explosion could deflect 2024 YR4 sufficiently if executed by 2029 to 2031. However, risks include unintended redirection toward Earth if mass estimates are inaccurate. Other methods, like gravity tractors using a spacecraft's mass to slowly tug the asteroid, or ion beams, are less feasible here due to the short timeline.
Countries preparing nuclear responses, United States and China leading the charge. The geopolitical landscape of planetary defense mirrors terrestrial power dynamics, with the United States and China at the forefront of nuclear-capable preparations for 2024 YR4. The U.S., through NASA and the Department of Energy, is actively modeling nuclear missions. Collaborations with national labs like Sandia have proposed launching two 100-kiloton devices via spacecraft to fragment or deflect the asteroid. This builds on DART's success, but escalates to nuclear for efficacy. Rationale: a lunar impact's debris could disrupt orbital assets by 1,000 times, threatening economic and military satellites. Public discourse on X, formerly Twitter, reflects this, with posts highlighting NASA's moon nuke plans as a dual-use technology, blurring civilian and military lines. China, via the China National Space Administration, CNSA, has accelerated its planetary defense program, forming dedicated teams in early 2025 amid 2024 YR4 concerns. Missions like Tianwen-2, launched May 2025 for asteroid sampling, and planned 2030 deflection tests incorporate nuclear options, leveraging hypersonic missile tech. China's dual-use approach, framed as space dominance, includes impacting NEOs like 2015 XF-261 by 2029. While not explicitly tied to 2024 YR4, these efforts position China as a rival to U.S. initiatives. Other nations, like Russia with its Burevestnik nuclear missiles, possess capabilities but focus on terrestrial deterrence. International cooperation remains discussed but hampered by U.S.-China rivalry, with UN oversight required under the Outer Space Treaty, 1967, which prohibits nuclear weapons in space but allows peaceful uses.
Challenges, ethics, and historical context. Nuclear deflection raises ethical dilemmas. Violating space treaties could spark an arms race, while failure might exacerbate risks. Historical examples beyond DART include simulations like the 2023 ISSI Burn Workshop on asteroid deflection, emphasizing kinetic over nuclear methods. Yet, for 2024 YR4, the timeline favors nukes, as deflection windows narrow post-2028. Public sentiment, evident in X discussions, mixes awe and concern. Hosts warn of Armageddon in real life while noting satellite risks. Conclusion: Asteroid 2024 YR4 embodies the precarious balance between cosmic indifference and human ingenuity. A lunar impact, while improbable, could disrupt our space-dependent society through debris hazards, prompting nations like the US and China to ready nuclear defenses. By learning from DART and advancing international frameworks, humanity can transform this threat into a milestone for planetary protection. As observations continue, the saga of 2024 YR4 reminds us, in the face of the stars, preparation is our greatest shield.